All right, to find a particular solution to an antiderivative, in other words, to find out which is the constant of integration, you actually need an initial condition. You need one point in it. If I can spell and get this to right. Initial condition. Okay, meaning a certain point that the antiderivative passes through. That'll help you find that C value so you know how, just which shift, vertical shift of the antiderivative family this particular one is. So for instance, if you have some equation where you know the derivative is this, okay, you can solve that using antiderivatives. You want to know the particular solution for that dy dx, this differential equation that passes through this point. Well, this is easier to solve by doing something called separating variables. I'm going to teach you a little bit about separating variables. And we're going to actually split these differentials up. Differentials are the dy and the dx. Okay, I'm going to move that dx to the other side. Okay, and now we're going to use what we just learned about antiderivatives to be able to solve this differential equation. And actually, you have to take the antiderivative of both sides, just like when you were doing related rates and you took the derivative of both sides of your equation. Same with optimization. You took the derivatives of both sides of your equation that you initially wrote. Then you do that for this. So if I take the integral, I'm going to take the integral of the right-hand side because it's a little bit easier. So if I take the antiderivative of this right-hand side, you get 3. The 3 comes down. We're going to use the power rule. So I'm going to add 1 to the exponent and divide by 3. And some of you will be like, oh, I don't even write the 3 because I get it. I mentioned in another video, I really need to write it. Now, some people feel very strongly about writing this x to the 0 there because it helps them. But you're going to bring the -1 down. You have to add 1 to the exponent, so you can't still be just -1. You have to go up a degree. So it has to be an x to the first. Divide by 1. I'm not going to write that one. I really don't. And then the plus c you need. Now, how about this other side? Remember we talked about that a little bit on our examples. There's really a 1 there, but notice that this one is a y. We're taking the derivative of y. So, antiderivative, the antiderivative of y. So this is 1 y to the 0. So I'm going to take the derivative of that, antiderivative, I misspoke again, of that. So bring down the 1 for the ride. You raise to the first power, and then there you go. Now, I'm not going to write a plus c on this side because if I have a c here and a c here, you can just subtract 1 over and they combine. So it's just one constant altogether. So we just write it in one place and figure out what that one constant is rather than each piece and then combine them. That just seems a little silly and tedious. So honestly, I never write this 1y to the first. I just write y. All right, equals x to the third minus 1x. Now, okay, that's silly. I'm not going to write the 1x. Nobody does that, right? So plus c. Now, it said to find the particular solution that goes through this point. Well, if we put in those values, that's an x and a y, right? So put in the x and the y, 4 for y, x is 2 again, plus c. Do you see right now you can find the c? So you can find that c value. Now, that's not the particular solution. That's the constant of integration, but that's 4 equals 8 minus 2 plus c. That's 6, right? So when I subtract it the other side, I hope you see that that's -2. Okay. So that's my constant of integration. My particular solution, my particular antiderivative is then y equals x cubed minus x minus 2, which is really nice if you have, say, a velocity and need to find a position function and you know one value of your position. This is exactly what that models. Okay, this models the same thing, but instead of writing it in differential form, it wrote it as a derivative, as an f prime, Newton's notation versus Leibniz notation. I write it like this. My children are playing with something in the other room if you're hearing banging. All right, so I'm going to rewrite that. I'm going to write it out front. Instead, I'm going to kind of write arrows and put that in front because it seems to confuse people. But we are going to separate our variables. That's what that's called. I don't know why the highlighter's out. We're going to separate our variables, and move them over. We're going to separate our differentials because those are the only variables to separate. Sometimes there's actually a y, not just a dy, but a y squared or something like that. You have to separate your variables. Okay, we're going to take the integral of both sides, the antiderivative. On this side, we just get y like we did before. And on this side, that's like an x to the negative 2. So I'm going to rewrite it. X to the negative 2 excuse me, I almost said dy. Dx. All right, so now I get y equals, because I already did that antiderivative, I still have to do this one here. I didn't take this antiderivative, so I'm going to do it now. Add 1, divide by negative 1, plus c. Remember, we only need one constant of integration because the one from one side and the one from the other side are going to combine to make one constant, so put them all together as one. Now, insert our particular solution. Remember, that's an x, that's a y. So we're going to put in y is 0. We're going to put in x is 1. And I violated my normal rules. I usually put my negative exponents down in that denominator. But you get 0. I got to move this up a little bit so I have a little more space, right? 0 equals negative, that's negative 1 over 1 to the first power, right? The negative I just moved out front, basically. And then that x to the first power, it's negative 1. It's negative 1 when all is said and done. So we have 0 equals negative 1 plus c. So c is 1. That's not our particular solution. It tells us what we have now. I changed this to y because I find it easier to do the integrals. But honestly, we started with an f prime. So what are we ending with? Instead of a y, we're ending with an f, right? An antiderivative, a big F. That's a big F deal, right? Okay, so our big F, our antiderivative for this particular solution goes through that particular point is 1 divided by, I'm changing this to x on the bottom, and it's negative, right? Negative 1 over x plus our c is 1. That's the particular solution instead of just this random going through one point. Now, I guess I should say that rewriting this is really negative 1 over x plus c. That's where I got, that's what this is about. So this is the particular, the antiderivative, the one antiderivative goes through that point up there, f of 1 equals 0. So that is the only antiderivative for this problem. It is not a family of antiderivatives. It is the answer that goes through that one point. All right, I'm trying something new here. I'm going to add this page in. We're going to find the general solution of f prime equals e to the x, where f of 0 equals 3. Just to have one more example. This is in your book, so if you want to follow along or read along, that is just fine. So if I'm going to find the antiderivative, if I'm going to find what f is, I take the antiderivative of e to the x. This is the way your book likes to write it. It's kind of a little bit different way to write exactly what I did on the other side. The other one is meant to kind of lead you toward differential equations. So if f prime equals e to the x, big F is equal to the antiderivative of e to the x. Well, the antiderivative of e to the x is just e to the x plus something. We don't know what that something is. But if you have an initial condition, you can figure out that something. You can put in your f of x, your y is 3. You can put in your x is 0, and then figure out your c by solving a linear equation. That's really nice. It boils down to a linear equation. Well, e to the 0 is 1, so your c is 2. So that's your constant of integration. It's not your general solution, which is another way to say particular solution. All right, and so our particular solution for big F of x is equal to e to the x plus 2. That is our particular solution. It is the equivalence of saying, hey, if that's your acceleration function, this is your velocity function, as long as you know that at time 0, your velocity is 2. Another way to think about that is saying, hey, if this is your velocity function and you know your position, your initial position, your starting position, when time is 0, is 3, figure out what the position function is. If this is your derivative, find out your antiderivative. Go backwards in your derivative order, basically. So that leads us to, right, so with that, we're going to do this example that led us from that past one, where I kind of talked about those initial conditions being velocity and acceleration. So it says this ball is thrown upward with an initial velocity of 64 feet per second and initial height of 80 feet. Well, what does that tell us? It tells us velocity at 0 is 64. But what's another way to write velocity? But S prime, okay? Because that's how we do position. S prime is 64. What is this saying? The initial height, meaning that at time 0, is 80. So in other words, it's saying at time 0, your height is 80. At time 0, your height is 80. At time 0, your velocity is 64. That's just two different ways to write that. Now, there's one piece of information that they don't actually tell you, but it is there. It's always there because we're on Earth, okay? The other thing is that acceleration, because of gravity, I'm trying to figure out where I'm going to write this. I'm going to write it down here. Acceleration, because of gravity, at any time, actually, is negative 32. Okay, I'm going to put it at any time, not 0. Sorry, I put 0. But it is true that at 0, it is also that. So that's another way to write A of t is the second derivative of position. Or, something moved, I'm sorry. Or, in other words, that, I must have bumped it with my hand, equals negative 32. Another way to write that is it's the derivative of velocity equals 32. I kind of prefer that one, but it doesn't really matter. So, if I want to solve this problem, I need to use antiderivatives to get backwards to position. So I'm going to start with what I know. I know this function. I know that the acceleration is always negative 32 feet per second squared. Okay, feet per second squared. I'm going to write that in. So if I want to go backwards and find velocity, I have to take the antiderivative of acceleration. Because if I take the antiderivative of acceleration, go backwards, I can find my velocity. Just like if I were finding velocity, I would take the derivative of position, and then to find the derivative of to find the acceleration, I would take the derivative of velocity. Sorry, that was hard to get out. I just have to think backwards now. So I need to take the antiderivative to find my velocity. So I need to take the antiderivative of negative 32 dt. Well, that's just negative 32t plus something, but we don't know what. It could be plus 10, it could be plus 8, it could be plus 40, I don't know. But if we use our initial condition for velocity right here, this is velocity, right? That's velocity, so let's use our initial condition. Velocity at 0 should equal 64. So this is velocity, right? V of t is equal to negative 32t plus c. So put in that information. V of 0 is 64. Put in our 0 for our t, and then we can figure out c. C is 64. Okay, so now I know that velocity for this particular function, that's why it's called a particular solution, is that. That's our velocity function. And now that we have our velocity function, we can go backwards and do the exact same thing. We're going to take the antiderivative of velocity, and it's going to give me my position. That's a t. If it's hard to read, that's a t. Okay, so if I take the antiderivative of negative 32t plus 64 dt, I just use the power rule. Negative 32 t to the second divided by 2. If you can write negative 16t squared, all the power to you. I find that I need to write it. Plus c, and that's our position function, because now we went backwards. We took the antiderivative of velocity, gave us position. So, okay, oops, that's not working the way I wanted it to. All right, so you can hear my children, I think, in the background. All right, so now if we put in our initial condition, we said that S of 0 was 80 up above. So let's put it in. That's negative 16. Okay, I simplified my little fraction there. I'm going to put in my 0 squared. Okay, that makes it easy. 64. I love putting 0 in because 64 times 0, everything's easy. Plus, we don't know what C is. It should equal 80. My S of 0 is 80. Hey, guess what C is? It's 80. So now I know that my function for position, which is what the question asks, my position function is equal to negative 16t squared, okay, because I simplified my fraction right here, plus 64t plus, oh, I don't have room for 80, plus 80. I'm going to rewrite that all so you can actually read it. So my S of t is equal to negative 16, it has to be negative, 16t squared plus 64t plus 80. And there we have it. That's our position function. And we found it using two antiderivatives. We had to use two, but there you have it. Okay, so it's going to get a little crazy. But now you can answer the question, the second question, when does the ball hit the ground? Because now you have your position function. Oops, I missed my one. So when does the ball hit the ground? Well, that would be when the height is 0, right? Or when S is 0. Oh, there's a little thing up in the corner. It's not letting me write. It's a little function. It keeps popping up little things it wants me to do. Okay, so 0 is equal to S of t. When does that hit the ground? Solve it. That's a quadratic equation. Wow, that doesn't look like a t at all. Let me try that one more time. Okay, t squared plus 64t plus 80. You can solve that in many ways. You can factor, you can use quadratic formula, you can graph it and find the zeros. But you should get t is equal to negative 1 and 5 seconds. I hope we can, that doesn't even look like a exclamation point, so let me get rid of it. I hope we can all agree that we can discard negative 1 seconds, so it must happen at 5 seconds. There you go. I'm going to let you solve it on your own, but that's the end of that. So that's the end of this section. I would strongly suggest doing some of these problems in your book. There aren't CUDA sheets for it. I have lots of answer keys. I just posted all of the answers for the book so you can find them. If you get stuck and you need solutions, I can text you those, email those, not text you, email those, and just let me know what you need. Thank you. See you soon. Keep working hard.